Yes, good morning. So we are live recording and also on YouTube. So first of all, thank you all for showing up. It's the last day of the course, and I before we start, I just want to say that if you haven't sent your selfie yet, and if you want to do it, feel free to send it to me by email. And also, please try to stay until the end of the course because we'll try to have an informal chat and closing uh, um, comments. And also to, of course, thank the speakers for these very nice 2 weeks that we've been learning about quantum information thermodynamics. So without further ado, Matteo, thank you again, and you have the stage.
Thank you very much, Gabriel. So welcome everyone to this last class. As I mentioned in the chat, if you have any questions about what we've done in the previous classes, please feel free to either raise your hand or write them in the chat. So this is a quick summary or recap of what we did last time. So if you remember, what we did is to kind of specialize the general resource theory framework to the situation where there are no memory effects. So we specialize thermal processes to Markovian thermal processes, and we saw that this is actually a way to connect this kind of abstract framework with a very widely used framework to describe thermalizations, which is the one based on master equations. So we discussed a little bit about what these equations are. We gave some very simple examples, and then we discussed a little bit about how do you now describe what are memory effects in thermodynamics using the tools that we developed in the previous classes. And in particular, we saw that there are, of course, stronger constraints. If you require that there are no memory effects, there are certain non-equilibrium transformations that can only happen if there are some of these fancy memory effects at play. And these memory effects physically typically involve a situation where you're interacting with an environment and then there is some kind of a backflow of information. So you interact with some parts of the environment and then those parts of the environment come into play later on. And in that sense, the description is of course more complicated. But however, if you do not have control on those kind of memory effects, or if the environment is large and the interaction is weak, so that effectively those memory effects can be neglected, as it is often the case, then everything can be described by these master equations. And we saw that then we need to refine a little bit our constraints. So these thermal majorization constraints needs to be refined and made into a sort of continuous version. And we also saw that within master equations, it's very useful to define entropy production inequalities. And we saw how we can go from this notion of continuous majorization to a whole family of entropy production inequalities that can help you decide if a certain out of equilibrium transformation can happen or not without memory. And yeah, so this was maybe the main idea of what we saw last time. And for this last lecture or class, we are going to switch gears a little bit. And we are going to talk about this kind of fine boundary between classical thermodynamics and quantum thermodynamics. So if you want something that is small scale, but doesn't, some effects that are small scale, but do not really require quantum effects to show up, and those that are somehow intrinsically quantum. And of course, the devil is in the details. So to actually point out and pinpoint what is that exactly is quantum mechanical or deserves to be called, truly quantum is a contentious issue. But it's also an interesting one because as in quantum information, in other disciplines, we really want to know what is different because the laws of nature are fundamentally quantum and they are not classical. So in this class, there will be two parts. So in the first part, we will see certain features that we discussed also in some of the previous classes and Nicole discussed. And we will see that to an extent, these are common to classical and quantum scenarios. So first of all, I would like to quickly connect thermomodularization to the second law so that we kind of conclude that part and we see that, you know, what's somehow the standing of thermomodularization is this strange, why do these strange constraints emerge? Is it because of quantum mechanics or other reasons? We will see Landauer principle. We will see how it is common to classical and quantum theories. We will briefly discuss about the origin of the second law as well in classical and quantum settings. And we will see that there are many similarities. And so in the second part, we will say, well, then if there are so many similarities, what's different? No? And I will propose only two possible answers to this question. One is about the definition of fluctuations of quantities such as work and heat, which is a complicated issue quantumly, even though it's very clear what's happening classically. And secondly, I will briefly tell you about this notion of strong non-classicality known as contextuality, and you know the kind of role that it can play in thermodynamics. And then I will conclude with like a last slide on what's next. And you know, if you're interested in following up on this course, where could you find more material and so on. And then we will have a quick chat with Gabriel, Nicole, and I mean everyone else. So that's the basic plan. And of course, again, feel free to write any questions in the chat at any point. So first of all, I would like to point out how do we actually go from all of these fancy thermomodularization constraints back to what we know, which is the second law. No? So what is that we saw? We saw in the previous classes that if you're out of equilibrium and you got a quantum state which is diagonal in the energy basis, and the probability of occupying the different energies is given by a vector P. There exists a thermal process that maps this quantum state to some finite quantum state with some different energy distribution Q, if and only if P is thermomajorizing Q. Okay. So now, of course, this is very different from the second law. But it shouldn't be so surprising because we are really dealing with an out of equilibrium scenario, and macroscopic classical thermodynamics was never meant to, you know, give you a complete description of that setting. You know, this unique entropy function that tells you if a transformation can happen or not, which is defined as a function of, you know, volume, temperature, pressure, and so on, is really defined at equilibrium. Okay, so. So not so surprising that there are so many other constraints at play in this kind of setting. However, let's focus only on equilibrium and let's see how we recover the second law in the standard form. So I'm going to consider now only equilibrium states, and now I will actually allow the Hamiltonian to possibly depend on, you know, maybe different at the beginning and at the end. No? So I have an out of equilibrium state, which is this gamma. So you have some probability distribution, which is the Gibbs or equilibrium distribution with respect to H, and then H is whatever is the Hamiltonian of the system at that point in time. No? And now consider what happens if you ask the question if there exists a transformation from some gamma H to some gamma H prime. No? And we know how to deal with this question because we need to construct these thermomajorization curves. No? So these are these curves where in the y-axis we are putting the partial sums of this probability, of the probability at play, and on the x-axis we are putting the partial sums of the Gibbs factors. So let me say e to a minus beta ei relative to whatever Hamiltonian we are talking about. Now the ei is the energy spectrum of H, so the energies of this Hamiltonian, the eigenvalues of this Hamiltonian. And now So what's nice about equilibrium states is that their thermomajorization curve is actually a straight line. So if I now here just write Z of H, which is just a partition function, so the sum of all the Gibbs factor for the Hamiltonian H, so I get some number, and now I put it here on the x-axis, no? And here I just put 1, which is the sum of all possible probabilities. So this gives me some point, okay? And now the thermomajorization curve, you can check easily that it's actually just a straight line. No? And then we can, if we want, just continue it like that. All right. And now if you, now you can do this with different equilibrium states with different Hamiltonians, no? So for example, you could say, okay, now I have my Hamiltonian H prime, so I'll do the same. So I will put here my partition function with respect to H prime. This defines a point, which is going to be here. And then I draw the corresponding curve. All right. And now thermomajorization still holds. So if you can go from the state represented by the red curve to the state represented by the blue curve, it must be the case, and in fact is equivalent to the case, that the first curve is all above the second, okay? But now it should be pretty clear from the plot that, you know, the curve of gamma, say gamma H, is all above the curve. Say that this is the curve, yeah, this is the curve for H, and the blue one is the curve for H prime. So, so the curve of gamma H is all above that of gamma prime, gamma H prime, if and only if, well, if and only if the Z point of H comes before the Z point of H prime, no, the ZH point. So if and only if Z of H is smaller or equal than Z of H prime. Okay, this should be clear from the plot. However, we can then multiply by minus kt and, sorry, take the log and multiply by minus kt, and we're gonna get then this relation. The minus kt, the log of Z of H, it's now bigger or equal because of the minus sign, minus kt log of Z of H prime. But now if you now remember the definition of equilibrium free energy from thermodynamic textbook, this is exactly the equilibrium free energy for H, and this is the equilibrium free energy from H prime. So we went from thermomajorization to just a single constraint, which is that the equilibrium free energy must decrease in the process. So in this way, you connect this non-equilibrium description. You see that, well, when I consider it in the equilibrium case, then everything boils down to the kind of relation that I knew already. So there is a question in the chat. I don't see why there is only one point in the curve. Well, so there are various points, actually. So there is a point for each of the partial sums. However, all of these points lie on the same straight line. And this is basically because when I consider this kind of ratios, this kind of ratios, so you can convince yourself that these kind of ratios are actually the slopes of these segments, okay? And now because pi is exactly the thermal distribution, pi, it's going to be e to the minus beta I divided by z or well, z of h, no? Okay, there is an implicit argument h, no? So this is 1 over z. So in fact, these curves are f slope 1 over z, and this doesn't depend on I, so it doesn't depend on which, which segment. So this curve is joining many little segments, but they all have the same slope, which is 1 over z, so I get all the way to 1. Sorry here for a little bit of mess. I wrote over something else. Okay, cool. So, okay, that's what's happening. So we recover the second law in the standard equilibrium form. On this point, I would also want to refer you to this paper if you're interested a bit more in all of these questions of the relations between, all of these generalized entropies that appear in the resource theory and kind of the standard unique entropy that emerges at equilibrium. So this is a nice paper to look. And maybe one point that this argument also makes is that thermomajorization is really about being out of equilibrium. It's not necessarily about being quantum mechanical, okay? It's not that things are different because they are quantum, things are different because we're describing a system that we usually do not describe in standard kind of textbook thermodynamics, which is thermodynamic transformations between out of equilibrium states. And this is why these extra constraints appear, okay? So in this sense, nothing especially quantum is happening, okay? So this was the first point I wanted to make on this connection. A second point was that I would like to go a little bit into is about Landauer principle that you saw already before, and we can rethink about it now in this framework that we are now getting more familiar with, which is this one based on thermal processes or thermal operations, no? And what we're going to see is that actually also Landauer's principle is common to both the classical and the quantum scenario. So if you remember, Landauer's principle was really a principle about what's a minimal dissipation to erase information. And in particular, it can be stated as saying that the minimum amount of heat that needs to be dissipated into a bath at temperature T, if you want to erase 1 bit of information, is kT log 2, okay? Now we're gonna see how this very same bound emerges quantum mechanically, so that once again, there is no difference between classical and quantum at this level, at the level of this bound, okay? So first of all, recall the setting, which is going to be actually quite common, not to Landauer's principle and thermal operations, because in Landauer's principle we had a system, bring in some environment and try to kind of dissipate heat into this environment to erase this system, no? And this may recall you the very first definition that we gave in the course, which was the one of thermal operations, where you were given a system, and then what is that you do? You bring in an environment, you couple it to the system. So an environment with some Hamiltonian, whatever that is, the environment is thermal, that's the only thing that we know. And we couple it with the system, and then we throw away the environment to know what's the state of the system at the end. And the unitary was conserving overall energy, okay? Now, the question that we may ask now is how much, well, the question that Landauer's principle answer is how much heat is dissipated into the environment to erase information from the system. So how much Q is dissipated to erase. And erase, what essentially means is to reduce the entropy of the system. Now, because the idea of erasure is that whatever is the input, my map should send me to a specific deterministic output, so that the kind of the entropy of the output should be 0. Okay, this is what it means to kind of erase, because you're kind of you know, whatever was the input at the beginning, you have your blank state at the end. Okay. So actually, the whole bound is based on a very simple fact, well, on one fact, which is the following. If I consider the entropy of the system tensor of the environment, so this is the entropy before you're doing the coupling, this is exactly equal to the entropy of the system and the environment after the interaction. Okay. And this may be, so why this is the case? Well, this S is the von Neumann entropy, and this is due to the unitary invariance of the von Neumann entropy. Okay. And at first sight, this may look a little bit strange, no? Isn't it a bit of a paradox? I mean, you have a closed system and the entropy, you know, you're doing all of this interaction correlating with the environment. Why isn't entropy increasing? Isn't the second law about entropy increase of closed system? But now note that really there is no paradox. And the reason there is no paradox is that if I'm actually able to have full control of system and environment, I can of course reverse the dynamics, no? I just apply the reverse of the unitary. Every unitary can be inverted, no? So of course it cannot increase, no? Otherwise the problem would be in the opposite direction. When I do the time reversal process, the time reversal process then would be decreasing entropy, no? Which is even worse, no? So the entropy must be constant, because to the extent that I can control system and environment, I can reverse the whole dynamics. Okay. Now, of course, this is not what's happening typically. Typically, you don't control both the system and environment, and then entropy is effectively increasing for you. But this is, I will you know, mention this in the next slide as well. But now let's go back a second and prove Landauer's principle based on the fact that this entropy is actually conserved in the unitary process. Now, if I write the entropy of the system plus the entropy of the environment in the initial state, I know that this is just the entropy of system tensor environment by the unitary invariance that we just mentioned. This is just the entropy of system and environment after the coupling has happened. And now there is something called subadditivity of entropy, which is the entropy of this global state is smaller or equal than the sum of the local entropies. So this is smaller or equal than the entropy of only the system part at the end plus the entropy of only the environment part at the end. Now, the system part, for example, is this guy here. And the environment part you can get by doing the trace instead of on E, you do the trace on S. No? So these are the local states of the system at the end of the interaction. No? Now you can put things together here, and you get that minus delta S of the system is smaller or equal than the change of entropy in the environment. This is just rearranging the term, no? And putting, you know, moving them on the two sides of the inequality. Now I'm going to leave you as an exercise this fact that the change of entropy of the environment is upper bounded by Q, the amount of energy that goes into the environment, divided by KT. Okay? So we get the Q is bigger or equal than minus KT delta S. Okay. Now, if my initial state was maximally mixed and say a qubit, and my final state, rho s bar, is pure because I am resetting my state to a fixed blank state, for example, 0, then the change of entropy is minus log 2, and then you get Landauer's principle in the standard form. So if you're interested in more details about this kind of things, you can have a look at this paper here. They study also, they give you this proof, they study improvements on this inequality in the case in which your environment is finite dimensional, so you have a bound on the dimension of the environment and so on. But here, what I wanted to stress is, of course, that this inequality we now derived in a completely quantum setting is the same as classically. Okay, so Landauer's principle is common to kind of quantum or classical theories. It's exactly the same. Okay, so any questions so far about Landauer's principle or this derivation? So here is the solution of the exercise. You can find it in the note that will be posted online. So if not, let me just, okay, no, there is, sorry, a question. Should we care about the efficiency of the erasure? I mean, does it matter if we erase completely or partially the information? Does it make sense? So you can, so the way this was derived in this form, the first form, you can in fact apply even when you're only kind of partially erasing the information, no? Because if you say, well, maybe I just want to, have a pretty good erasure process. Maybe I just want to have epsilon, I don't know, epsilon 1 plus 1 minus epsilon 0. Okay, where epsilon is, I don't know, 0.01. Then you just compute the entropy of this guy. You get some numerical value. You plug it inside this formula. And then you get what's the corresponding bound on this process. And the bound will be a little less. Now you will spend a little less than log 2, but then you will be doing a not perfect erasure of information. I don't know if that was what you meant by the question. Cool. So I think it's also interesting to see that we have a second law classically and we have a second law quantum mechanically. They involve relatively different objects. In one case, we usually use the von Neumann entropy. In the other case, we would be using something like the Gibbs entropy, volume of microstates, and things look quite different. But then, also in this context, one can see very strong similarities between the way in which the second law emerges quantum mechanically and the way in which the second law emerges classically. So, of course, I'm not gonna give you any kind of exhaustive, description of this topic. It's a huge topic. People trying to, studying the foundations of statistical mechanics. But just this is one point of view. So when you consider something like we were considering just before, no, you have an interaction between a system and an environment, and then. So this is the state of system and environment at the beginning. And this is the state of the system and environment at the end. Okay. Now, we can kind of differentiate between two different ways in which this process may be described. So there may be what we could call a global agent or a daemon. And this agent is characterized by the fact that there is no entropy increase for him. What I mean by that is what we just mentioned a second ago, is that if the daemon, you imagine the daemon being an agent that controls both the system and the environment. So the daemon knows what's a state at the beginning, it knows perfectly raw SE, and the entropy that is computing is going to be some raw of SE. And then it knows perfectly, or it knows perfectly the entropy at the end. And these entropies are the same. Why? Because the von Neumann entropy is constant. Okay, I'm going to go back to this question in the chat in a second. Now, again, this is operationally meaningful. Because if we are this daemon, we can in fact reverse the old dynamics. And in fact, we are ourselves daemons to the extent that this environment is small enough. And because of the progress that we've been making in the laboratory and so on, we can actually have full control of small enough quantum systems. And then to the extent that we do have that control, everything is reversible. Now we fully control any kind of noise, and to an idealization, of course. We control the entanglement that gets created between system and environment, and we can reverse the old dynamics. Okay, so it actually makes sense that the entropy is constant because we can reverse the dynamics, so it should be constant. It's a reversible transformation. Okay, but however, as we have seen in the previous slide, we proved this equation here, which we can rewrite as delta SS plus delta SE bigger or equal than 0, okay, under a closed system evolution. No? And what does this mean? Well, it means if we are local observers, so this was a global observer, was able to control everything about S and E, including all of the correlations that gets created. But if we are a local observer or agent, meaning that everything that we control is only on the system or only on the environment, we don't control, system environments correlations and how they get created and so on, then we see entropy increase. Okay, and it's actually this kind of statements that we have in mind when we say that the entropy of a closed system is increasing. Okay, but as you see, the increase of entropy, it's coming about because we cannot have, or we don't have in general, or possibly all of the information about system and environment, especially so if the environment is very large. We may not only not control the system environment correlation, we may even not control the environment at all. Let me check now. There are a couple of questions in the chat. With the gas particle in the box, we needed work to erase the qubit information by pushing a piston. I don't really see how to erase information with heat in that case. Is it possible? So also in that case, so when you say, okay, you need work to erase the qubit information, in fact, that energy that you're talking about was getting dissipated into the external environment. This is how um, the erasure worked. And this is, yeah, this is basically because what you're trying to do is, in every time you're doing erasure, what you're trying to do is a 2-to-1 transformation. Now, independently of what's the input, you're trying to get the same output. No, but this is conflicting with the fact that at the fundamental level, everything is reversible. No, so what you really need is also some environment where the entropy there is increasing, no? So that you can have 1-1 transformations only because of that, while maintaining reversibility. I don't know if this is making sense, but somehow on the environment you're gonna have that at the beginning maybe you knew what, okay, let me not go into this, it will take a little bit to describe you the situation. But well, yeah, concerning your question in particular, I would just say, yes, you need work, but this is work that is being actually, it's energy that is being dissipated as heat. No, it's actually because you're erasing, you're using work, so your piston is up and then it goes down. So that work gets consumed, and this is energy that gets dissipated into the environment. And it's because of that entropy dumping that you can decrease the entropy of the system. No? You decrease the entropy in the system while increasing the entropy of the environment. And how do you do it? By dumping heat into it. So now the question was, the constant entropy during the time evolution just holds when the initial state is separable? No, it holds in general. So I could take any raw SE that is also initially entangled, and then I compute the entropy at the beginning and at the end, and entropy is conserved under any unitary process. So this could be X of, 1, 2, 3, etc. So multipartite system initially correlated. And then this is the same as entropy of U of X, 1, 2, 3, and so on. Okay. So, okay, so we see here that, no worries. Okay, sorry, there is another question. The increase of local entropy is a consequence of the separable initial start, right? Yes. So if you start with initial correlations, then you can get an inequality similar to this one, but you would have also you have an additional mutual information term. Okay, so this mutual information term, mutual information is a quantity, for people that maybe don't know, it's a quantity that quantifies the amount of total correlations, classical and quantum, in the initial state. And then basically this inequality here can be violated by an amount that depends on this I, the initial correlation. So in one thing that you can affect, for example, if you have system and environment, is you can decrease the entropy of the system, decrease the entropy of the environment to some extent, but while these correlations get somehow consumed. Yeah, so there are more general relations that you can write, including also the mutual information term. And this is the basis of all of these effects, like backflow of information of heat. No, if you have a hot bath and a cold bath, this kind of relation here. So when there is no correlation, will tell you that heat will necessarily flow from hot to cold. But if you add this mutual information term, so the initial state is now actually correlated between the two, then you can actually have a backflow, so heat going from the cold to the hot, so becoming even colder, And the maximum amount of this backflow is actually KT times this mutual information term here. So another question is, when you say local agent, you mean that locally both system and environment increase entropy, or just their sum, assuming separable initial states? Yeah, so when I meant local agents, I meant agents that do not control, that only control the marginal of S and the marginal of E, so the local state of S and the local state of E. They do not control the global state that also involves any entanglement between system and environment. So the law here, as it is derived, is that the sum of the two entropies must increase. So you can have that the entropy of one is decreasing, because one thing that you can do is to dump some entropy of the environment into the, some entropy of the system into the environment. So delta S would be negative and delta SE would be positive. And this is exactly the case of erasure, because in the case of erasure, you want the system's entropy to decrease. And you do so by increasing the environment's entropy, which, if you want, is basically this inequality here. And or you could even have the other way around. No? Cool. I think one thing that it's nice to point out is that, we're using this von Neumann entropy, and as I was mentioning, usually this is not it's not something that it has an immediate relation with, kind of textbook classical thermodynamics, no? But and so there is this thing that entropy is being conserved while your unitary process happens. But it's nice to actually point out that it was exactly the same classically. So let me briefly go through this. So classically, what is that we have? We actually have systems that are described in phase space, okay? So the kind of objects that we're dealing with is this gamma of t, where gamma of t is the phase space distribution at time t. So phase space is the space of position and momenta of your system. And in general, if you're describing, if you know exactly where it is, it's just a point in this big multidimensional space. Otherwise, it's going to be a distribution in this space. So this is going to be a phase space distribution, probability distribution at time t. Okay. And another piece of notation, let me call gamma of TVP. Okay, TVP just for our example. There could be other macro variables if you want. Let me define this guy here as the set of all microstates compatible with this particular macro state. Okay. So now consider this situation. So assume that at time 0, I prepared my system and I, with some temperature, some volume, and some pressure. And this is everything that I know about it. So my initial phase space distribution that reflects my kind of knowledge or lack of knowledge is just this gamma of TVP by definition. And now I'm doing an experiment. And the experiment is the following. I'm taking this TVP and then I'm, heating it up, I'm pushing a piston, whatever. I'm changing my microstate from TVP to some T prime, V prime, and P prime. Okay, at time equal 1 or whatever, some final time, no? Conventionally, let me call it 1, no? And now, again, as before, there were two descriptions. There was this global agent daemon description, and then there was the laboratory local agent description. Also, classically, you can make this exactly the same argument, no? So what I drew here is gamma 0 which is the initial probability distribution at time equals 0, okay, which is describing your knowledge about the initial macrostate. And now let's first focus on this demon's description. So how does a demon describe this kind of experiment? So what is a demon? Well, a demon in this context is an agent that is actually able to take this whole probability distribution and applies Hamilton's equations to it, okay? Which is the same situation as the other global agent demon that was able to take the initial state and apply the whole Schrodinger equation to it, okay? So if it does so, this demon will know that for any initial state, whatever the initial state is, there will be some final state at the end, which is the time evolved under Hamilton's equations. So good. So what's the entropy of the demon at the beginning? Well, the entropy of the demon at the beginning is Kb times the volume of gamma 0. This is just Gibbs entropy, right? And now the demon, as I just said, knows how to evolve each representative point inside gamma 0 through Hamilton's equations to gamma 1, okay? So then what's gonna be the entropy of the demon at time 1, according to the demon? Well, it's gonna be Kb, the volume of gamma 1, okay? And gamma 1 is gonna be some weird looking distribution in phase space. However, we know, and this is a theorem by Liouville, that the volume of the probability distribution in phase space under Hamiltonian evolution is conserved. So the volume of gamma 0 is equal to the volume of gamma 1. So the entropy of the demon is not changing at all. Okay. Again, this is operationally fine. If we were in the situation that we could actually control all of these microscopic degrees of freedom, we would be able to undo the whole evolution. So we would also be able to take T prime, V prime, P prime back into TVP. On the other side, what happens in the laboratory description? Well, in the laboratory description, again, I start with the same distribution here, which is gamma of TVP at time equals 0. However, now I don't describe the whole evolution at all. Everything I know about the final state is that it has temperature T prime, volume P prime, and pressure P prime. No? And now, okay. So one last observation that we need to make is that about this gamma prime here. What is this gamma prime? Well, this is a particular distribution compatible with T prime, V prime, P prime, okay? Whatever that distribution is, certainly is compatible with T prime, V prime, P prime because, well, because we know that the transformation that is happening is this one. And this is just described by the demon in this way, okay? And now we are ready to compute the entropy according to the agent in the lab. What's the entropy at the final time? Well, it's Kb, the volume of the probability distribution that the agent associates to the final state. And remember that it doesn't, apply Hamilton's equations and so on. It just, what is that he associates? The agent associates, or she associates, just the set of probability distribution, the only thing that the agent knows is that the final macrostate is T prime, V prime, P prime. So everything that the agent knows is that at some point inside this guy here, gamma of T prime, V prime, P prime. It's some point inside the set of microstate compatible with what the agent knows the macrostate is, okay? So this is by definition the entropy at the end, no? But now this guy is bigger or equal than KB, the volume of gamma 1. Why is it bigger? Well, because gamma 1 is just some particular distribution compatible with T prime, V prime, P prime. Whereas gamma of T prime, V prime, T prime is the set of all possible microstates that are compatible. So certainly, as I drew here in this plot, this distribution is contained inside gamma of T prime, V prime, T prime, just by kind of boundary conditions. So this is the crucial point, really, because then again, we are just using the fact that entropy is conserved. So the volume of gamma 1 is equal to the volume of gamma 0. And so this by definition is Kb, the volume of omega of TVP, which is the laboratory entropy at time 0. Okay. And now we just proved that the entropy in the laboratory is increasing, okay, which is the statement to the second law. And this is just a consequence actually of the fact that this entropy, the entropy defined as volume of microstate, is conserved by the microscopic evolution, plus the fact that we actually do not control everything about this evolution. No? And now we may say, well, but what's the right entropy? I mean, the laboratory entropy is increasing, the demon's entropy is constant. What's the right one? Well, essentially, if you erase the labels and we just erase lab here and we erase D here and we say, well, here entropy is increasing, here as entropy is constant. This is where all of demons, Maxwell's demon paradox are emerging, no? Because you can have situations where according to the laboratory agent, entropy is increasing, but then because for the demon entropy is constant, the demon can reverse it. And so if the demon is reversing the transformation, what would you see in the lab? Well, you would see a decrease in entropy. So the demon can violate the second law according to the laboratories. But the whole point is to recognize that the entropy is really defined according to what is your level of control of the system. And once you do so, then it's not particularly somehow surprising that this can happen, because you're violating my second law that I define under my own level of control. And if you're a microscopic demon that controls everything, of course you can trick me. Of course you can see as reversible something that I see as irreversible. So this is the arguments that were made, well, or at least my best attempt to reproduce the arguments that James makes in these couple of papers that, if you're interested in the foundations of quantum statistical mechanics, are super interesting. I would highly recommend them. But, what I also wanted to point out in this context is simply that, again, you have an entropy that is constant in time. And then it's, the origin of the second law from this point of view, it's coming about because of some loss of information, because of your lack of full control of, a microscopic system. And this is exactly the same classically as it is quantum mechanically. We see exactly the same analogies. This doesn't mean that everything must be the same, but at least on face value, the kind of arguments are very much the same. You can make them in a very similar manner. Any question about this? So with this, I finish the first part, so we can have 5 minutes break and restart at 4. And in the second part, we talk about a few aspects that are somehow actually different between classical and quantum thermodynamics, and or possible challenges that quantum thermodynamics poses to our classical worldview. In the meantime, of course, if you have any questions, feel free to post them in the chat, and I'll see you at 4 then.
YouTube chat is silent so far, but I've asked around, and if there are any questions, I can share them before we start.
Cool.
Okay, so no questions on YouTube though, but I guess plenty of questions here in the Zoom chat.
Mm-hmm. Sorry, I am reconnecting, so the orange square disappeared, and then I need to reopen the chat. Okay. Okay, so there are a few questions in the chat. So the first one is, what about the correlations in the classical case? In the quantum scenarios, it plays an important role since it breaks the entropy additivity. Classically, where exactly they appear? I would say that at least in a broad sense, classically and quantumly, correlations play the same role. Not in the sense, of course, that they are equivalent because entanglement is stronger and there are some things that can only happen because the state is entangled, but this would bring us into another direction. But what I mean by that is that, for example, in this paper I was mentioning by James, it's called Gibbs versus Boltzmann entropies, here on the bottom right. And actually is talking about the Gibbs entropy, which is very much like the Voigt-Norman entropy, so the logarithm of the volume of microstates, and this is preserved under your closed system evolution, the Hamiltonian dynamics, whereas the Boltzmann entropy was defined in terms of not of the global probability distribution over phase space, but the local ones, okay? So if you then and that Boltzmann entropy is increasing under closed system evolution. And then if you think about it, the analogous of the Boltzmann entropy is basically just the sum of the local entropies, no? Because what it is just you're taking the global distribution, you're throwing away the correlations, and then you're computing that entropy, no? Which is exactly in a sense what we're doing here, no? At yeah, in here. So yeah, so in this sense, there is quite a few analogies between the two cases, and in both situations, I would say that the interpretation is similar, that these are entropies that are relevant for agents that only control the system locally. They do not control, say, any global observable across various systems or system and environment. So there was another question. For the quantum case, what is the analog to the phase space distribution you need to make the argument? For example, would the negativity of the Wigner function have an impact? Yes, so this is a very good question. So in terms of the Wigner function, I haven't thought about this particular argument there. For sure, it has been used to compute thermodynamic corrections to classical predictions. This is actually the way the Wigner himself introduced the function for the first time. But in terms of the argument, yeah, the issue here is that you don't have a phase space description of the system unless you kind of force it using the negativity. But you could make a similar argument also at the level of the Hilbert space itself, no? Because so one way you could reason is that I'm in my quantum lab, and then everything I control is some set of observables, no? There may be, for example, some set of local observables, no? And then you have some unitary evolution, and you may define, so you move your quantum state rho into some other quantum state u rho u dagger. But now you may define the entropy of the demon would be just the Voigt-Norman entropy at the beginning and at the end, and that would be conserved. But then you may want to define an entropy at the end, which is just going to be, if you wish, a laboratory entropy, S lab at the end. You may define it as the maximum of entropy among all states, such that this state here has the value of those observable that you actually see, no? So maybe a bit more clearly. So this is the daemon description, and then there is the laboratory description, where everything you know is that you add some uh, observables, or 1 or 2 or 3, and their value went from little o1, little o2 to little o1 prime, little o2 prime, and so on. No? This is everything that you actually control about your quantum system, for example, a bunch of observables. And then you can associate an entropy at each time as just the maximum polynomial entropy of the states that are compatible with what you see. Now, this is the minimally unbiased choice. No? And then you would have that, and in the laboratory description, things are, of course, entropy is increasing, and even though the von Neumann entropy is decreasing. And in this way, you can kind of tune what your entropy is depending on what kind of control you have about the system. So maybe this is a way I would do it personally. But I don't exclude that you could also go through follow your suggestion and use the phase space description instead.
So Matteo, there is a question on YouTube. So Adalberto Parisi is asking, so concerning your argument that irreversibility comes from the lack of control of both system and environment, he's asking essentially if there's a consensus on this, if there are counter arguments to this reasoning.
Um, well, there is a sense in which there is this famous paradox in thermodynamics, now, which is the microscopic laws are reversible, and thermodynamics is about irreversible processes. So there must be somewhere in between where irreversibility is entering, no? And if you, of course, there may be attempts to define intrinsic notions of irreversibility, especially quantum mechanically. Um, um, say, I don't know, the collapse of the wave function or something else. But as far as we know, all of the laws are reversible. So at the global level, if I look at the global picture, I look at the state of the whole universe, this guy is evolving unitarily. So the entropy cannot increase, or I can reverse any process if I take into account large enough a number of degrees of freedom. So from that point of view, irreversibility should come from some information that is lacking. So it seems to me, at least, that there is these two binary choices. Either there is some intrinsic loss of information, or the information loss is subjective to some particular class of observers, even though it can become effectively objective in the sense that we all sorts of agree about what are these macro states. And so it's not that it means that things are completely not well defined. Then, of course, there are many different approaches to think about the foundations of statistical mechanics, but I'm not sure if there is disagreement, at least on this point, that in a sense, either there is some intrinsic loss of information, but then it's also some physics that we don't know about because we think the quantum mechanics preserves information, or irreversibility is generated in some due to lack of control, which is very much, the case for the kind of agents that we care about and the kind of situations that we care about. At least this is what I would say. Maybe some other people would have another opinion. I don't know. But yeah, it's a tricky question. There were some. Okay, there is another question. If there were timestamps associated with the initial and final states, then for the daemon, both the timestamps would be equivalent, whereas in the lab, one could differentiate the timestamps based on the increase of entropy. This seems like there is a connection between the passage of time and entropy. Is this argument valid? People have been speaking for a long time about the relation between entropy increase and the arrow of time. Let's say I don't judge, and I'm not able to judge to what extent people are being able to push this kind of arguments. Yes, so sorry, I cannot say more on this. But yeah, I mean, there is somehow a relation, no? So another question is why gamma zero is equal to, so gamma zero was the distribution at the end. Why is it equal to the set of all possible microstates compatible with VPT? It seems that this imposes the initial state as to be a microstate evolved by an Hamiltonian compatible with a specific microstate of a given distribution. Well, this was just a rule of the game as I set the problem out. I just said, imagine that both you and I know that the initial state of the system is some equilibrium state with some volume, pressure, and temperature. No? So we kind of have the same knowledge at the start. But then, you have your super mega computer and you can actually compute the Hamiltonian evolution for each microstate and know what's exactly the shape of the probability distribution of a phase space at the end. Whereas what I do, I just push some pistons or, change the volume and so on and so forth. And everything I know at the end is that I let the system kind of relax to equilibrium with some final volume, pressure, and temperature, and this is everything I know. And now I'm comparing the entropy that you would define with the entropy that I would define, which are associated to two very different operational situations. You have the information to actually reverse the system to its initial distribution, and I don't. So in this sense, for me, there is this entropy increase, and for you, not. But then you could consider other situations as well, where you even know more better than me the initial state, for example. But yes, that you could do. Cool. Okay. I hope I didn't forget any. You're not very convinced. Maybe we can talk about it later. But this is how I define the problem, basically. Just I assume equal knowledge for the daemon and the agent at the beginning, and then I saw what happens from there. Oh, was there another question that I forgot? No. Okay. Okay, so in this very last part, let me just say a few things about quantum effects in thermodynamics. So for now, we talked about things that are common in a general sense between quantum and classical thermodynamics. And in fact, this is, in a sense, maybe a bit disappointing, but the broad results are common. So the kind of super pillars of the theory are common to classical and quantum thermodynamics. No, so we saw Landauer principle. We didn't talk about it, but there is also, of course, famously Carnot's efficiency. So when people started to think about engines at the quantum scales and compute their efficiency or maximum efficiencies, those were bound by, again, the Carnot limit. This is not to say that everything is the same. And of course, predictions are different due to the difference of different predictions are different in specific models. No? And I would say probably the most famous example is the difference that there is between the classical and the quantum harmonic oscillator. No? In fact, some of the very first pioneering results in quantum mechanics were about the difference in specific heats in classical, according to classical theory and according to quantum theory. And actually, in this regard, if you're interested in what kind of difference this makes in quantum engines, you can look at this paper here. So these are implications for thermal machines. Okay. So maybe the kind of question that we are really asking is not so much about, if I do thermodynamics based on microscopic classical models, of course I get predictions that are different than what if I do the same with quantum microscopic models and I kind of build up the statistical mechanics of those. But what we are really asking is if whether there are core differences that are challenging not just a particular mechanical model, but they are really challenging in a strong sense the whole classical worldview. No? So we could put it as core differences challenging not a particular model, but the whole classical worldview. So, and this is what I'm going to talk about in this last part. And I'm going to propose two challenges. One has to do with quantum fluctuations, and the other has to do with contextuality. So the first one is about the definition of quantum fluctuations of work. And again, we need to just quickly remind what's the situation classically. So classically, again, you have phase space, you have a probability distribution of a phase space that represents your knowledge. And then for any representative point S of 0 in phase space, you have some Hamiltonian evolution that brings it to some other representative point S of t, so that the whole distribution moves from, say, this one to this one. And now what's happening is that, the work, I'm now thinking about closed system evolution, not because it's the only interesting case, not at all, but because it's actually the simplest. And if you cannot answer the question even in the simplest case, then it means that there is something interesting going on. But the amount of work that I need to put into the system to do this transformation, given that I started from state S of 0, is of course deterministic. It's just the energy of the point S of t minus the energy of the point S of 0. Okay, so if I put things together, I get the work is associated to a random variable, which is distributed according to the initial probability distribution, so the probability of being in some state S of 0. So this is where all of the stochasticity happens, because the dynamics is deterministic. And then the work is the corresponding W of S0. So now I've got this probability, I know what values it takes, and in principle, there is no special problem in defining quantum fluctuations of work, okay? Now, let's see what happens quantumly. So quantumly, you immediately have an issue, which is, it can be that at the initial time, the energy is not even defined. So because you see that what we're doing in the previous definition is to take the energy difference between the final and the initial state. So energy at t equals 0 may be undefined. Okay, so for example, if I take the Hamiltonian to be just 1, 1, meaning that the excited state has energy 1, the ground state has energy 0, and then imagine that I take as initial state the state plus. Okay, and then I do a unitary, for example, an Andermatt gate that maps my system from equal superposition of 0 and 1 into the ground state 0. No? So now it's easy to know what's the average amount of work required for this transformation, which is just the average energy at the end minus the average energy at the beginning. Okay, so this is the amount of work that is needed to do the transformation. And the average energy at the end is 0. The average energy at the beginning is 1/2, because 0 is energy 0 and 1 is energy 1. So the average change of energy is minus 1/2. And this is fine, but what we really wanted to know is fluctuations. What are the fluctuations of this quantity? Okay, so there is one solution that is, I think, still probably the most used solution, which is measure the energy at the beginning and measure the energy at the end. And this is the 2-point measurement scheme that Nicole was talking about. Okay, but now you see that there is at least a potential problem here, which is the following. So let's consider exactly the case that we just studied. So I start with my state plus, I do my energy measurement at the beginning, and then I get with probability 1/2 the state 0, and with probability 1/2 I get the state 1. Now I do my unitary evolution. There was this Adamar unitary, so that at the end of the evolution, my state is either plus if the input was 0, or minus, which is 0 minus 1 over square root of 2, if the input was 1. Okay, and now I do my energy measurement at the end, and again I get 0 with probability 1/2, 1 with probability 1/2, and the same if the state at the end was minus. And then you see that what's happening is that with probability 1/4, I find my initial energy to be 0 and my final energy to be 0. No, because I'm kind of following this path here. This is probability 1/4. This is what's happening. And then actually it's 1/4 for every other case. I go from 0 to 1 with probability 1/4, from 1 to 0 with probability 1/4, and from 1 to 1 with probability 1/4. So now if I define my work as just the difference in energy between the two measurements, you see that on average, in this 2-point measurement scheme, the average work in this transformation is 0. And this is a little problem in a sense, because I wanted to describe the fluctuation of the process above. I introduced the measurements, and now the measurements change everything. They change, including the expectation value of the observable I wanted to study the fluctuations of. Okay. But maybe this is everything we can do. This is one point of view, no? That this is the best we can do. But certainly, this TPM scheme it kind of has this issue of giving wrong between quotes averages, but it's also intuitively appealing. I mean, if you apply it when there is no superposition, it's quite clear what happens. So when there is no superpositions, you don't have this problem of having the average being different than the one you'd expect. And actually, the 2-point measurement scheme is describing a stochastic process where you jump from certain energy to other energies. which is exactly a kind of jumps that that you would imagine should happen because of your quantum evolution. Um, so okay, you could say, okay, this TPM scheme may be good for certain things, and it may have these properties that maybe I would like to remove. So it's a natural question to ask, is there a different scheme that doesn't have this issue but kind of preserves the good aspects of the TPM scheme? So in more specifically, you could ask, can I find a scheme such that it respects certain simple properties? So first of all, for every quantum state, you want that the scheme is going to return a probability distribution P rho of W, so some work probability. So probability distribution, and this probability should be linear in the input. Well, it should be linear in the input because this is just, what should happen if the kind of stochastic interpretation you're giving to the process works. Now, if I put as input with probability 1/2 one state and with probability 1/2 another state, I will just get the corresponding mixture of the fluctuations. And then I want a probability distribution because I wanted to define the probability distributions of quantum fluctuations of work. Second condition that you may want to put is that if rho is diagonal, then this P of rho that you're introducing should be the same as the 2-point measurement scheme probability, because this is really kind of makes intuitive sense, this 2-point measurement distribution, as long as there are no superpositions. And the 2-point measurement scheme, if you apply to a Gibbs state, as I think Nicole has told you, defines fluctuations that respect fluctuation theorem, Jasinski's equality. So when things are diagonal, everything seems fine. So we would like to recover what we know from the diagonal situation. And finally, we would like that your probability distribution gives you the right averages, in the sense that if I average this quantity, I would like it to be just the energy difference between the final state and the initial state. Because if I didn't want to define fluctuations, I would know at least how to define averages, and this is how I would define averages. So I would like to recover this condition. Okay, so then the question is there a scheme that satisfies these three natural assumptions? And the answer is no. If you want to know more about this, you can check out this nice paper. In fact, there are various schemes that can satisfy 2 or the 3 of these conditions. So you can see as the 2-point measurement scheme as being basically a scheme that satisfies assumption 1 and 2. There is a different proposal, not I think very used, which is called the operator of work, that satisfies assumption 1 and 3. And then there are other schemes that are based on kind of dropping the first assumption, and these are based on what's called quasi-probability distributions. Where you renounce the idea that you can actually find any meaningful notion of probability distributions associated to fluctuations, and you allow for these objects to also become negative. Okay, and I think the way I like to think about what's a really core issue here at play is that basically in quantum mechanics, there are no joint probability distributions associated to non-commuting quantities. This is something that we very well know. No, we know that there is no joint probability distribution for position and momenta, for example. So what are the non-commuting observables in this case? Well, if you think about the process in Heisenberg picture, what is that you're trying to do? You're trying to measure the energy at the beginning, which is h of 0, and then you're trying to measure the energy at the end, that in Heisenberg picture would be doing the measurement of this other observable here. I now incorporated the unitary evolution in the observable. This is what the Heisenberg picture is. So if you think about the protocol in Heisenberg picture, what is that you would like to do is to measure the Hamiltonian at the beginning and the Hamiltonian at the end. And these two guys may be non-commuting. And if they don't commute, and what you want to do is then take the energy difference between the outcomes of these two measurements. But then, the issue here is that there is no joint probability distribution. Exactly as there is no joint probability distribution associated to position and momentum. No? And then you can either say, okay, I'm gonna bite the bullet, I'm gonna do the first measurement. I know that I'm going to completely change the distribution of the final measurement that I would have obtained if I didn't do the first measurement. So you kind of accept that this big disturbance, and then you can define fluctuations and probability distributions of fluctuations, but these are not the somehow of the process that you wanted to describe, which is the kind of untouched process. Or you say, well, I know from position and momentum that one way to kind of think about these problems is to say, well, I cannot define a probability distribution for position and momentum, but I can still define a quasi-probability distribution for position and momentum. And this is useful in certain contexts. Its negativity can be interpreted as as a quantum signature. And then you could go along with this idea of defining quasi-probability distributions. Okay, so but maybe as a final comment is that there was some debate, I think, during the classes that there is no unique definition of work and heat. Okay, and it seemed a little bit surprising. I mean, we have been doing quantum thermodynamics for a long time. How is it that there is no unique definition of work, heat? And it seems like these are very concrete things. They should have some unique definition. But I would argue that because of this situation here, actually we kind of know that there is no unique definition, no? Because we're really having the problem that what we want to define is not clearly defined quantum mechanically, and there are various way out, and depending on the way out that you choose, you can get a different answer, no? But because of non-commutativity, while all of these different ways that you have to get out kind of become one and the same, if you look at the commuting scenario, because of non-commutativity, there is no unique answer. There may be a more useful answer in a certain context and a more useful answer in another context. And unfortunately, I think this is gonna stay in a sense. It's kind of a feature of the problem. So if you're interested in more details about all of these various definitions of work, you can have a look at this review on how to define fluctuations in the presence of superpositions and these various ways that people have been proposing. There are quite a few of them, and you can make your own mind on this topic.
So Matteo, maybe
Yep.
I can interrupt with a question from YouTube.
Yeah.
So Matteo Savi, he's asking about the role of weak measurements and whether, specifically in the TPM, but whether that could give any advantages in comparison to strong measurements.
Yes, so if you do weak measurements, so weak measurements, for those of you that maybe don't know, so these are another class of measurements where instead of measuring the energy at the beginning projectively or beginning and the end projectively, which is a strong measurement, you're gonna only encode a tiny little bit of information about the system in your measurement device, so that you're getting out very little information, but at the same time, the disturbance that you induce on the system, which is kind of the collapse of the wave function, is going to be very limited. So the quantum state of the system is going to change very little. And weak measurement is a kind of limiting process where you're looking at what happens as kind of first order, where this disturbance is kind of infinitesimal, and the information you're getting out is infinitesimal. Now, in the context of fluctuations of work, so one thing that you can do is, but there are others, of course, is, as I said, in the 2-point measurement scheme, you have the system, and then there is a unitary evolution, and here there is a projective measurement, and here there is a projective measurement, and that's all. And then you look at the energy difference. What you can do instead is to, instead of doing this projective measurement, you can do a weak measurement here. So why would you do that? Well, you would like to avoid this strong disturbance of the system, which destroys your initial superposition. So if you do that, then you can define a quantity that respects property 2 and 3, but it's not a probability distribution. It's a quasi-probability distribution, and it's related to something that is called weak value. So yes, so it's certainly an interesting thing that you can do to look at weak measurements and what can they do for you in this kind of context. And indeed they have been used in this regard. Yes. Any other question? Okay, so last topic, contextuality. So this I leave it, in a way as a challenge. No, this is definitely a challenge. It's really hinging upon the fact that non-commutativity, a strong non-classical property, not clear how to define these fluctuations, and it's definitely a place where one can and should look, I think, to think about the differences between classical and quantum thermodynamics. So, but how could you resolve this problem by considering the measurement as a thermodynamic process themselves? I guess it depends on what you mean by resolving the problems, isn't it? Definitely, it's interesting to look at what's the role of thermodynamic role of measurements. People have been thinking recently about this. Yeah, considering some work or heat during the measurement. Yes, this is something you can do. Consider that if I do a projective measurement, I'm not putting any work into the system. No, the energy of the system is constant. Not only the average, but any moment of the energy is constant. But it's being dephased, meaning it's being the off-diagonal elements of the density matrix are being destroyed. So the quantum parts of the quantum state is being destroyed, even though there is no energetics to it. But people have been thinking along the lines of, if I need to do a projective measurements, then I need some device which, where I can encode the information, what's the entropy of that device, and so on and so forth. I don't know. I don't know. I mean, this no-go theorem is here to stay in a sense. Then any answer that you can get should somehow fit within this theorem in any sense. But yeah, I don't know. Could we consider the existence of the free conditions in a scheme as a resource? I don't understand the question, sorry. So these are free conditions that can be easily satisfied classically, and people would like to have in a scheme that measures work fluctuations, and they cannot be all jointly satisfied. But yeah, I don't know what you would mean by considering them as a resource. You can consider to what extent one of them breaks, and you may break approximately one and see how much you can preserve another and see the trade-offs, but fundamentally they are impossible to satisfy jointly. Okay, but yeah, sorry if I didn't reply, feel free to ask me again at the end. Okay, contextuality, different way of challenging maybe the kind of classical worldview. What is contextuality? So this is an abstract notion of non-classicality. And to explain what it is, there are various ways. I decided for the one that I think maybe it's not optimal, but it's the quickest by far. So consider a quantum protocol that goes as follows. I prepare a quantum state raw. I send it through some machine that is doing some transformation, which in general I can represent by some channel epsilon. It could be some unitary dynamics, for example. And then I have a measurement device that is doing some measurement M with outcome Ks. This is known as a POVM. For those of you that don't know, so these are a way to represent measurements. These are positive operators and sum to one, to identity, sorry. And each of these each element in this family of operators represent a possible outcome. And so these are generalizing the idea of projectors in projecting measurements, and the probability of any outcome is just given by the trace. This is the Born rule of mk with epsilon of rho, which is the evolved or rho under your dynamics epsilon. So the question that we are asking here is if there exists a stochastic, kind of classical stochastic description of this experiment. So we are asking, can it be, this quantum protocol, can it be represented by a stochastic process? So what do I mean formally? I mean the following, that these three boxes here, so instead of the preparation of the state, if I can describe the whole experiment stochastically, I'm imagining that I can actually sample from some probability distribution P rho of lambda. So lambda are some set of classical states. And in the quantum description, I'm saying I'm preparing the quantum state rho, but in the stochastic description, I'm just saying I'm preparing some lambda with a certain probability, which is some P rho of lambda. No? So this lambda is being prepared by my box, and then it goes inside the box that represents a channel. And of course, quantum mechanically, this is a quantum mechanical evolution. We are describing it as some coherent evolution, say Schrodinger equation or whatever. And we are asking if there exists a stochastic process that describes what's going on. So instead of the channel, you're going to have a probability distribution, which is a set of transition probabilities. It tells you what's the probability that if you're in lambda, you jump to lambda prime. So you should imagine then the lambda is being prepared by the first box, then it's being updated by the second box with some probability p epsilon of lambda prime given lambda to some lambda prime. And now it's going into the final box, which is the measurement. And what does it mean that this measurement is described stochastically? Well, it just means that there is some response function, P, M, that what it does is just telling you what's the probability of an outcome K, given that the state was lambda prime. So the state that is entering was lambda prime, okay? So here the machine is outputting k. And now instead of the Born rule, in this context, you have that is you would like to reproduce this pk as the sum of these various stochastic processes that by propagation of probability is gonna look like this double sum, where you got the probability that given that you prepared raw, you're sampling lambda times the probability that, given that you were in lambda, you jump to lambda prime times the probability that given that you end up in lambda prime, you output outcome k. And if I sum over all possibility, these are various, this is various stochastic processes that are happening. There is no interference effects or anything. And I would like to know if I can represent what I see in my quantum experiment by means of such a description. Also note that a stochastic interpretation requires certain properties from this object, this P of rho of lambda and the other. For example, P of rho of lambda should be a probability, as I implicitly said while I was describing this kind of scenario. And on top of it, it should be linear in rho. Why should be linear in rho? Again, because this is what it should do if it's compatible with our stochastic description. No? If I prepare the given state rho with a certain probability one half and some state sigma with some probability 1/2, then it means that I'm sampling from this guy with probability 1/2, and I'm sampling from this guy with probability 1/2. So I can define a new probability from which I'm sampling, which is just the convex combination of the two that I started with. No? So basically the propagation probability tells you that it should be linear. And the same for the other two. P epsilon of lambda prime given lambda should be a matrix of transition probabilities, linear in epsilon, and PM likewise should be when I sum over all k, I should get 1 because the probability of some outcome happening is 1, and it should be positive and it should be linear in the measurement. Now, I'm not saying that every quantum protocol can be described in this way. In fact, that's not the case. But if so, if there exists such description, I'm going to say that the quantum protocol admits a non-contextual model. And if it doesn't, I say that the protocol is contextual. So if you're familiar with the idea of contextuality, this may be not a very familiar, the most common way to introduce this whole business. I used it for kind of pedagogical reasons, but the deep reason behind this equivalence can be found, for example, in this paper here. But anyhow, this is the definition that we use in this class. No? If a protocol admits its stochastic interpretation, I say it's non-contextual. And then it's clear that now what I'm saying is that I'm going to call the protocols that are contextual are non-classical in a strong sense. They are non-classical in the sense that there is no way of describing them by means of a classical stochastic process. Okay, so it's a meaningful notion of what it means to be non-classical. However, I would like to kind of put immediately a warning here. Warning sign is that it kind of looks like, because we are describing things as a stochastic process, it seems that the definition that I'm using of what it means to be non-classical is exactly the same as saying that there is some superposition, no? Because everything is stochastic. Now, when is it that I cannot describe some quantum protocol in a stochastic manner? Well, whenever I'm dealing with quantum superpositions of different states, for sure I will not be able to give this description. So this may be an idea, but this idea is not correct. Quantum superposition sometimes can be described, admits a description in terms of a stochastic process. So it's not in one correspondence with just saying whenever there is some superposition is non-classical. No, it's a bit more refined than that. It must be some superposition that engenders some experimental outputs that cannot be described by a classical random process. And I think it could be nice to quickly see an example of this, which is a simplified version of the two-slit experiment, which involves an interferometer. Actually, maybe too many. So here you got two input ports here that I'm gonna call left and right. Here I'm gonna put a mirror, and here I'm gonna put another mirror. Okay, and say I'm gonna put a photon in, and I'm gonna check where it's coming out. So this is called a Mach-Zehnder interferometer. Okay, and then the quantum description. Well, I'm gonna give a kind of maybe simplified quantum description. Is simply the following. At the beginning, if I put the, say, photon here in the left branch, it goes through the mirror, and the photon is going to come out in a superposition of the right branch, or the, if you want, the black branch and the red branch. So it's gonna be in a superposition of these two states. And then it goes through the second mirror, and the same transformation happens. So this is basically like doing an Hadamard transformation. You just create this superposition. Then you apply the same unitary a second time, and because this unitary is its own self-inverse, if you apply here, this is the first mirror, and this is the second mirror. So I get the result that if I put the photon in the left, I get it out in the left again. So in the red branch. Okay. Even though, of course, if I measure in the middle, I will see that with probability 1/2 it's in the left branch, and with probability 1/2 it's in the right branch. And sometimes people say, well, this is okay. Well, let's say this process clearly involves quantum superposition. So one could say, well, clearly this cannot be described by a stochastic process. And one could even have the idea that to say, well, you see, after the first mirror, I find the photon with probability 1/2 here and with probability 1/2 here. So it must be, if I give a stochastic description, it must be that the mirror is letting the photon pass with probability 1/2 and is reflecting the photon with probability 1/2. So this explains why, if I put a photodetector in the middle between the two mirrors, I find the photon in one branch or the other with probability 1/2. But then one can argue, well, you see that this doesn't work, because if that was the case, then the photon would keep going, and it would come from the left with probability 1/2 and from the right with probability 1/2. And because the mirror is either reflecting or transmitting with probability 1/2, I would find the photon here with probability 1/2, or the photon here with probability 1/2, which is not what happens in the quantum case, because what happens in the quantum case is that you have quantum interference and cancellation, so that the photon always comes out of the left branch, the red one. However, this argument just tells you that this particular stochastic process doesn't work. And in fact, there are simple ways to define a stochastic process that does work. And one of them is the following. I'm not saying that this is what's happening. This is not at all what's happening. But in terms of our question is, does there exist a way to describe this process stochastically or not? And one way is the following here. Imagine that the photons come into qualities. Kind of the black ones and the red ones. Just to say two things. I'm not saying the actual color of the photon, the frequency, just saying, they have two different properties, no? And when I input photons, actually I don't know, but with probability 1/2, I'm inputting a photon which is black, and with probability 1/2, I'm inputting a photon which is red. No? So with probability 1/2, my initial state is a photon on the left, and it's a black photon. And with probability 1/2, my photon is on the right, is still on the left, sorry, because I decided to put it on the left, but it is red. And then the rule is simply the following. What the mirror does is that it lets pass every black photon, and it reflects any red photon. So if the black photon comes in, it lets it pass. Whereas if the red photon comes in, it reflects it. So then you see that now this is after the first mirror. If I do the measurement here, after the first mirror, what I would see is that with probability 1/2, my photon, I don't measure what is this hidden color of the photon. I just measure if it's on the left or on the right. And I will find it with probability 1/2 on the left and with probability 1/2 on the right. Now it goes through the second mirror. And again, the mirror lets pass, transmits the black photons, and it reflects the red ones. So now if I measure it at the end, I see it with probability 1 on the left. And this was exactly the quantum situation. If I measure in the middle, I would find it with probability 1/2 in any of the two branches. And if I measure at the end, I find it with probability 1 on the left branch. And here there is no superposition. It's just a stochastic process with some where we have added this degree of freedom in the photon, and it's able to describe this experiment. So this experiment would not be contextual according to the previous notion. So not contextual, even if you have superposition. And this is, okay, I think for many people this is obvious, but I think it's really important to stress because it's a bit subtle to find these quantum effects. It's not just to say whenever there is superpositions in the quantum states, I'm done. So then the question would be, are there then thermodynamic protocols that are contextual according to the previous definition, meaning that do not admit any stochastic description, meaning any non-contextual model. So the answer is yes. So one example is looking at work extraction. So you just take your quantum state and then you do a unitary on your quantum state. And then we're gonna do the simplest thing. We're just gonna define work as the energy change in the system. And then in the linear regime, meaning that I'm taking my unitary and I'm looking at kind of the limit of a small action. So this unitary is actually going to be just the identity plus some small correction. So this is called the linear response regime. We can have quantum mechanically that the amount of work is scaling with G. The amount of work we are getting out is scaling as G. So linear in your small parameter, on your linear response parameter, even though in every non-contextual model, the same work is bounded by something that is quadratic with this coupling parameter. Meaning that if I were to plot how the amount of work I'm getting scales with this parameter, I would see that quantum mechanically can scale linearly, and in non-contextual model it needs to scale quadratically. So for G small enough, I would see a violation. So the amount of work you're getting out quantum mechanically, it's too large to be explained by this stochastic process. Okay, so sorry for the delay. So let me just briefly say, I put here one slide with some what's next slide. So thank you for having resisted through this whole second part of the course. There is, of course, a lot of material out there that you can look if you're interested in knowing more about these topics. Of course, I'm available for any follow-up questions that you may have. You have my email. Here I just put a list of possible places where you can find some material, starting with, of course, the website of the mini course, this nice initiative that I think Gabriel is going to talk about or remind you about the QIT Thermo Reading Group that came out actually from this mini course. There is then a video discussion recently from the annual Quantum Thermodynamics 2020 conference, Quo Vadis Quantum Thermo, if you're interested about discussions on what direction is this field taking. And then I just put a list of some possible places where you can find extra material. There is, of course, a lot there. But these are nice possible, introductions or places where you can get some further information. And of course, a very incomplete list at that. But I think with that, I would like to thank you for coming to the course and coming for this second part. And then I think I will just give back the word to Gabriel, that I would like to thank in my name and names of Nicole and everyone else, I think, in the course for having organized and put together this this fantastic opportunity to talk about quantum thermodynamics.
Awesome, Matteo. Thank you so much for another great lecture. So let me just say a couple of things before we wrap up. And before anything else, I mean, if you guys, all the participants, if you could open your cameras, just so we can see your face, maybe take a nice selfie, and also as a way of thanking the speaker. I mean, first of all, Matteo and Nicole, thank you so much for taking the time and the effort to prepare this course and to teach this course. It has been really fantastic. I think the course, by all kinds of measures, it has been a huge success. There's been a lot of people interested, also a lot of people enrolled in the course and staying until the end, which I think is really great. The course is there's people from all around the world. So I put a map today, this morning, in the website showing kind of the diversity of people from all around the world. And I think that's really great. And also this material will all remain online forever, hopefully. And I think that could be really valuable for future students and future researchers. So I just want to quickly say that the YouTube channel that some of you use to view the videos, that YouTube channel may not keep the videos on, because that's the official YouTube channel of the of my university. But the YouTube videos that are on the website, they are from a different channel and they will stay on. So the website will be sort of the main place where you can find all the YouTube videos and together with the lecture notes and so on. They will remain there for future reference. I guess other than that, I just want to thank you all very much. And again, thank Matteo and Nicole. So yeah, and I guess also advertise this QIT reading group as well. I think that's a great initiative by Cheyenne, which I believe will um, be, I mean, really, really interesting and really, really powerful. And I mean, it feels to me to be a nice experiment that could lead to very, very amazing things. So I'm really excited to see how this reading group will develop. Okay, so I guess if I'm not forgetting anything, so thank you all very much. And yeah, so we see you around, maybe in the reading group. Cool. Thank you.
Thank you. Have a nice holiday. Take care and stay safe.
Yeah, nice holidays too.